Okay, we're going to learn about motors this time. So let's set this up. So, and we're fact for this course, we're only concerned with one kind of motor, and that's what's called a DC servo motor. There's many kinds of motors. We're just going to play with this one. Okay, and this can all get incredibly sophisticated. So you just have to handle one type. So what are some of the parts? The rotor, an iron cylinder which is free to rotate. Okay, that's kind of this inner part here. All right, and it has rotating coils, all these windings embedded in the surface. This is called the armature winding. Okay, then you have the commutator. Okay, that are these two brushes. So current is coming in to drive this thing. It comes in here, it leaves out here. Okay, through these brushes. Okay, then we have the stator, the stationary outside electromagnet. That's this big thing. Okay, and so what creates the current, or oops, wrong word, what creates the flux density, the magnetic field, is this current, which comes in and it's winding around, leaves out here. And so you will have basically north here and south over here. Okay, so the flux is going this way across. Okay, now here we're looking at this thing more electrically. So this whole process is going to have, there's a voltage we're calling here EF. This will have all these windings will have their own characteristic resistance, inductance, and that'll create the magnetic field that drives through here. Okay, we're not developing models, so we're just going to say the magnetic field is a function of this thing IF. All right. Now let's look at the force or torque in the system. So what you're seeing here is if we take a look at this one, the current's coming out so you have this winding, so this long conductor, and once again you have comes up here, goes down there. So for every rotation about the rotor, you're going to get two conductors. So it's coming out like so. All right. So if you use the right hand rule, you go up here. Magnetic field goes across. So wrap, and we're going this way. So there is a force going down this way off of this point. Well, that's going to create this torque. So R cross F. So that part of the picture makes sense. Now, here's R cross F. Now the equation was V L cross B times IA. Okay, so everything was all perpendicular, so this just works out to be LVB IA. But this B is just some function of this current. We don't know what this is. So here's what I want you to understand. There's a motor property, Km. So torque is proportional to the current coming in, IA, and there's a motor torque constant, K sub m. This is given, okay, it's property of the motor. So in an exam, I'll be saying if we're using a DC servo motor, I'll give you Km. It relates to IA and it produces torque. All right, back voltage. So back voltage is velocity cross magnetic field times L. So let's look here. I'm going to look at this conductor. So this is going in. Notice my pencil going in. So that's where the current's going. All right. But this thing is rotating this way, so the velocity is going up. My fingers, so I'll just put this. Here's the velocity going this way, with the magnetic field going that way. So V cross B comes up. So I have current going in, but increasing voltage goes against the current. Well, that's exactly what we have. So the current's coming in, doing this thing, and so it's losing voltage, higher voltage on this way than it leaves. So is how that is. All right. For an exam, what you need to understand is if you go through this, V cross B times L, velocity is R theta dot. So back voltage is related to angular velocity. And so all of this stuff is summarized in a constant, K sub B, related to the back voltage. So EB is KB, and this constant will be given to you, theta dot. All right? So this is what rather than trying to go through and figure out all of these cross products and trying to make diagrams that let you figure out what's going on, which is these are standardized constants that are given, and I will be giving them to you. All right. Now, having said that, I want to take a moment and notice the trends. So we have found that there are sort of things that are similar or analogies. We had force is like torque, and we noted that it's like current. Well, notice current creates torque. All right. And we noticed, like, if we go back to translational systems, if I have a spring and I push it, changing position creates force to flow through the spring. Okay. So force, here we had force and current, but angular rotation, okay, so change in position, that's what we're having here. As this thing turns, that creates voltage. Okay. So notice voltage, when you have a voltage drop, that makes current flow. So angular rotation creates a voltage drop, which draws current down through the motor. Rotation, voltage. Okay. So position, voltage, they work the same. And that forces the current to flow. So I am now done with introducing motors. These are the two things I want you to walk away with. And this is easy to understand. Position drives voltage, and that forces current to flow. So we have current, torque. They're analogies of each other. I'll see you next time, and we're going to do a motor problem.